need of help have, I think most have seen me, at least those who seem eager to do well. I hope that more of you will come see me before it's too late. That's the main thing, right? You don't want to wait till the last moment to say, oh, I need help, because I can't help you at that time. The learning curve is far too much. So we have some ways to go before we wrap up rotation problems. And one of the areas of rotation that typically causes some issues is when you have what is called static equilibrium. So static equilibrium, simply put, for example, is you have a ladder leaning against a wall. So if the conditions aren't right, this ladder could slip. Or you may be jumping on the ladder even if the conditions are right, and the ladder could slip and you might fall. So what holds the ladder up? Okay. And there are many examples like that. I'll illustrate them as I go along today. The idea is that static equilibrium, which gets a bad name from engineers actually, because it's seen as boring. But it is actually a very interesting area, because all the stuff that you have learned so far really come in handy as you try to set up and describe problems regarding static equilibrium. So I'm going to try and get to that. I'm also going to warn you that that's an area where kids have trouble. So please, raise your hands and come to me whenever things are not going very well in static equilibrium, because the conditions are a little bit more demanding than what you have done so far, and even in the homeworks that I've assigned. Now, I'm again seeing a drop-off in questions regarding the homework sets, and I hope that's because you guys are able to do the homeworks better rather than doing anything funny. So do seek help if you are not sure about homeworks. Now, before I get to statics, let me start with stuff we have done before and kind of go over them one more time, at least some of them. The idea being that I'm not entirely certain to what extent students have taken in the concepts that we have done. So, you remember one thing that we talked about is the no slipping condition. So let's have a brief discussion about the no slipping condition, because there are cases when you have to be aware that you can't use it, and then there are most cases where you actually do use it. So I have given you a problem in this current homework set where for part of the problem you don't use it, for part of the problem you use it. Okay? So, and these problems are by any means difficult. So basically what it is that suppose you have a ball, and this is not a good drawing, and the ball is rolling down some incline. All right? So this is the way the ball is rolling, and that also means that presumably, as we discussed last time, that means that the center of mass is moving forward. So the ball is going forward. And the ball has a radius r, let's say for the sake of argument, to keep matters simple. And let's say you measure the angular speed of the rotation of this ball as it goes down, and you find it to be some number that we can represent by omega. So omega is 2 pi over t. We already know that. So all you need to do to get omega is measure the time taken for a complete round circle as the ball rolls down, and that's your big T, and from that you can infer what your omega value is given T, and the unit for that is going to be 1 over second. So far we have not brought in no slipping or any such thing, right? This is just normal stuff. No slipping means, as we discussed last time, that the center of mass velocity, so this is the center of mass velocity of this ball, so let's call it VCM, is related to this omega via the relationship R omega. That's what no slipping means. And I also told you that our studies are pretty restricted. Restricted in the sense that we are talking about the contact of this ball with the surface at one point and no more. So in other words, this point contact is just at one point P. That is a very special assumption that we make, because we know very well, as we discussed earlier, that if it's not a single point contact, if the wheel is flattened, which they always will be, we assume it's not, but in a real life situation the wheel will be flat when it touches the surface, then one has to be a little bit more careful, because the nature of friction and rotation will be affected. We are not going there. So that's the reason why I'm reminding you that what we are doing is very special and restricted. So this statement, the fact that this is a point contact and this contact is just for the sphere to be able to pivot forward, is what this no slipping condition means. That specifically means just that. Okay? Don't make a mistake about it, because this is where often people go wrong, because 90% of the time even books are not very clear about it. So no slipping condition basically means you have a single point contact, and it's about that point contact that this thing is rolling forward. But there are two independent processes going on. One is the fact that the ball is rotating. Okay? So rotation is one process. And the other is the fact that the ball is moving forward, which is what we call the ball is translating. And it's only when you have this single point contact, you have the no slipping condition, where the center of mass of the ball's translation is tied to the omega with the radius r. The other thing is that, as I told you, nothing moves at this point P. This point P is a contact point about which the ball pivots, but there is no movement in point P. Point P is where everything actually is momentarily at rest. So therefore, the fact that you can have a point P where this ball can touch the road surface and nothing moves essentially means there's got to be a friction. So it's the presence of this friction that allows you to have potentially the no slipping condition. So you need the friction for the no slipping condition. But what kind of friction is it? Remember, I told you that point P is just a pivot point. There is no slippage or anything. So this friction is not kinetic friction. This friction is actually your good old static friction. All right? So these are very important layers of concepts that we have built in the last two lectures that I want you to go over one more time. And just be very careful, because these are very simple mistakes, conceptual mistakes that one can make. Any questions so far? Because now I'm going to take you to another point. But if this is not clear, we'd rather have it clarified. Okay, so hopefully it's clear. But as I told you, let's take off here. There are two processes going on. One is rotation, one is translation. And these two processes don't have to be related. They don't have to be related. They are only related when you have this no slipping condition and when you have this point friction coming in. That's when they're only related, as far as we are concerned. So can there be a situation where we can actually realize the fact that they are not related? Well, yes. And that's exactly one of the problems I gave you. So let's say, for example, that this ball is coming down the surface, and we have the no slipping condition here. So we have friction here. So we have a mu s, and the ball is rolling like that, and then you have a center of mass velocity. And so this part of the incline is what I would call as rough. Rough basically means you have a mu s. Rough is the code word for saying that you have a mu s. But now, suppose that you hit an ice patch. Buffalonians should be very familiar with hitting ice patches. So I don't expect you guys to make a mistake when you encounter this problem. So when you hit an ice patch, there is no friction, right? The ice patch means there is no friction. Your friction has gone away. So now the question is, what's going to happen to your rolling ball? Or for that matter, your wheel in your car? Well, the point contact assumption still remains valid because this is a rigid body. That's why the word rigid has been used for so long. It's a rigid body. It's not a body that can be flattened, that is floppy. It's not like that. It's a rigid body. It can be a very hard material. You can imagine that for which the flattening at the contact surface is so small that you can think of it as a point contact. That's what we mean technically. So over here, something interesting happens. Now what is the interesting thing that happens? Over here, the ball will continue to slide forward. The ball will not stop, right? Because it's icy. So we all know that you can, if you are moving along, if you hit an ice patch, you'll continue to move along. There's no problem there. So if the ball was moving along here, there is no question that the center of mass will be moving along. That's a no-brainer. But what happens to the rolling? Do you guys think it will continue to roll, or do you guys think that it will not roll anymore? Remember, there is no friction anymore. How many of you think that it will continue to roll? Somebody raise a hand and lowered it. That's not allowed. What about you guys? You guys are not voting yet. You think it will continue to roll? Nobody else thinks it's going to continue to roll? How about you guys here? It's going to continue to roll or not continue to roll? You think it's going to continue to roll? How? Yes. You think it's going to continue to roll? So the rest of you think it's not going to continue to roll? Are you sure? This is actually a pretty tricky problem, because if you think about it, it's not trivial. But what I want you to think, in case you are unsure, and it's natural to be unsure, is the fact that the rotation process is actually not generally related to the translation process. So for example, let's say you have your car wheels. Your car wheels are rotating because you are powering that rotation process with your engine, right? If you hit an ice patch, your engine will continue to operate. So think about it. Your car wheel therefore can continue to rotate. There's no problem there, right? But you won't be going forward necessarily the way you want to, because the V equals R omega, the effective no slipping condition, is no longer valid. So the point is, at this point, rotation is still there in general. So you have no reason to assume that rotation stops. Okay? Because it's an independent process. So rotation is still okay. Translation, it can still go forward. Nothing can stop it from going forward. Because there was inertia. It was moving on ice. It was moving on a rough surface. It hit an ice patch. So what? It's going to continue to slide forward. So translation basically means slide forward is okay. So that's okay too. However, because you have hit the ice patch, these two have now become independent processes, so V is no longer equal to R omega. All right? So this is the main message that I want you to understand, that when you are hitting a patch where there is no friction, your primary point is that V equals R omega is no longer valid. However, the rotation process and the translation process, they don't necessarily have to stop. In fact, they probably will not stop. So this is a very important point that I wanted you to think about, because I personally feel it's quite non-trivial to be able to appreciate this point. So in other words, if your kinetic energy over here, if your total kinetic energy in the rough patch, let's do the calculation. So let's say kinetic energy in the rough patch, should have 1/2 mv center of mass square. That's the kinetic energy associated with translation. And you also have kinetic energy associated with rotation, right? So I is the moment of inertia for a sphere. I told you for a sphere I is 2/5 mr squared. So I sphere is 2/5 mass times r squared. And if I have a disk, for example, that's 1/2 mr squared. So we can check out whatever case we want. So the kinetic energy when you have a rough surface is going to be 1/2 mv center of mass squared plus 1/2. Let's say you have a sphere, so you have 2/5 mr squared. So this is the ball, so this is the sphere case. Okay, and then you have omega squared, but we already know that v center of mass is r omega, which would imply that omega is v center of mass over r, which means I can write here v center of mass over r. This is square and this is also square, which means this r square and that r square will cancel. So this series of steps would be okay as long as I'm doing a no slipping condition calculation. So now you see the kinetic energy for a sphere, what happens? So we have mv center of mass squared in both the terms. Here you can see this 2 and that 2 will cancel. So I have 1/2 from the first term, and I have 1/5 from the second term. So that will be 10, which means 5 plus 2. So therefore, it will be 7/10 mass times v center of mass squared. So this would be the kinetic energy on a rough surface for my sphere. The number, however, would be different if I had a disk, right? Because I would do the same calculation. So this is for a sphere. Let's call it sphere. So if I do the same calculation for a disk, rough, for a disk, then this would be once again 1/2 mv center of mass square, right? Plus 1/2. Now I have 1/2 mr squared for my moment of inertia, and once again, if there is no slippage, I have v center of mass squared over r squared. As before, the r squares will go away, but you see the coefficient is different, so the energy will come out different, everything else remaining the same. So I can write then as mv center of mass squared, and then I have 1/2 plus 1/4. I have 1/2 plus 1/4. So that means 2/4 plus 1/4, so that will be 3/4. So you see the expression for kinetic energy for a disk now will come out different, because we now have a different value of the moment of inertia. So these are very straightforward tricks of the trade, and this is where I really do not want you to make a mistake, because I want to be testing you on these things, and I want you to be able to glide through them smoothly. So what happens when you have a smooth surface? When you have a smooth surface, all the nicety that we did can't be done anymore. Why? Well, Think about it. So kinetic energy for a sphere, when you have a smooth surface, meaning an icy surface in this case, I would once again have 1/2 mv center of mass squared, and I would once again have 1/5 mr squared, but I have to write here omega squared because this omega and this v center of mass are not going to be related because of no slipping condition not being valid because it's smooth. And similarly here, you can't do this step where we could simplify because we had the no slipping condition being valid. So this is actually something, this is a part of the calculation that goes into one of the problems I assigned you in your homework that I assigned yesterday. All right, I have already done quite a bit of stuff with you guys, but let me move over to another delicate area where I find that usually a little bit more exposure helps a lot. So let's go back to the problem where you have some kind of a pulley. So in the past we have ignored the detail of our pulleys when we have done pulleys with Newton's law. Because the pulleys were moving really for our purposes, we were only considering translational motion, and the pulley's rotation had no role to play. We didn't have to worry about it. We ignored it. Now though, the pulley's rotation matters. So here you have the pulley, you have a massless string that's wound around the pulley, and then you have, let's say, some mass here. This mass, let's say, is big M, and this has, let's say, some radius r. So the way it's working is that this thing is turning, let's say turning that way, as this thing is turning, this mass is going downward. That's our problem. Very simple problem. However, even though it's a very simple problem, we want to be able to work out this problem in a way that makes sense. So let us do a free body diagram of what's going on for small m. I would just write FBD to remind you that we are doing a free body diagram. So we are actually resurrecting everything we have learned from chapters 4 and 5 and so on. That's what this free body diagram is all about. So we have an mg, which is a downward force. We know that, right? We have a tension T, which is an upward force. And then we have an acceleration downward here because it is going down. All right? Guys, would you shut up? Both of you? It's been going on for a while. But you may think you are very silent, but you are not. Okay? I catch you talking. Zeros in the quizzes today. Watch out. So here we have the thing going downward. So mg is the winning force going downward. All right? Tension is my upward force. And then I have ma. So this, by the way, is what I would refer to as my force equation. This is my force equation. So in these problems, the thing is that force equation alone isn't enough. You also now need to construct a torque equation. And this is something we went over last week, on Thursday. So what is a torque equation? Well, this thing is quite a leap of faith here. You have to understand that this wheel, think about this wheel. Let's draw a picture of this wheel itself. This wheel is turning because of two things. First of all, there is an axis here and that allows this wheel to turn about that axis. So if you could take a look from the edge here, then you will see that it's like two discs with an area to have the coil have the string wrap around, much like a yo-yo. And then you have something here, and then you have something on the other side, and then you have an axis. So it's turning about that axis. That's how this wheel is turned. What's happening though is that you have the string coming down, and as far as this wheel is concerned, and this part is not simple, as far as this wheel is concerned, it'll feel a tug because this one will feel a downward tension force. Just like small m feels an upward tension force, this fellow, the wheel itself, will now feel a downward tension force. And because it will feel this tug downward, that is what's going to make it turn the way it does. All right? So now what you have is that you have to now calculate this torque because you have the ideal conditions. You have everything needed to calculate a torque. You have a force, and this force is acting with respect to this axis here. So you actually do have a given perpendicular that connects to this force. That's your radius r. And because of that, this thing turns, and it also has a moment of inertia I. And as this mass speeds up, going downward, it has an acceleration a, which is this here a, which correspondingly results in an angular acceleration alpha. And to impose the no slipping condition, you must never, never, never forget that a is r alpha. That will be your equivalent no slipping condition in this problem. Remember, when I said no slipping condition, I talked about delta theta, delta x is, I talked about delta x as r delta theta. You can divide by delta t, so v is equal to r omega. I also talked about a is equal to r alpha. All three are manifestations of the no slipping condition. Okay? So therefore, we have a no slipping condition here, and the corresponding torque equation that we must have then is going to be T times R, right? That's the torque being generated. So that's like equivalent of mass times acceleration. That's the equivalent of force. And on the right-hand side, you'll have the equivalent of mass times acceleration, which is the moment of inertia I times alpha. Okay? So that, in fact, is your torque equation. And this, in fact, is your all-important third condition, without which you're fried, because you have to now use the no slipping condition to be able to relate those two. All right? So now you see we have everything in place to be able to do our calculations. I've done this before. I've done it on last Thursday, but I'm going over it one more time because this is a soft spot for most students when they learn it, especially if they've never seen it before. Because for the first time in your life in physics, you actually have three simultaneous conditions that you've got to cook up. So far, if you think about it, in every case we have done two conditions, and here you have three conditions. So most times what I find is that the students would do this equation correctly, they would probably fumble through this, and they would then forget about that and completely fall apart. Okay? So don't do something that's stupid. In fact, I'll take off additional points if you do something that's stupid. So now let's see. So we have this equation and that equation, and we now should be able to do some work. So this is a disk here, so it's 1/2 big M times R squared times alpha, right? So therefore, I can write the tension T as 1/2 M times R times alpha, because one of these R's would go away, right? And then I can take this T and put it back into equation 1. So therefore, I'll have mg minus 1/2 M, this is big M, R alpha is equal to small may or A. And I also know that A is equal to R alpha. So therefore alpha is A over R, which means now to speak the same language, I need to get rid of this alpha. So I would keep it as mg here minus 1/2 big MR, but I have alpha as A over R. So this is my alpha here, times is equal to m times A. The R's will cancel, and you can do the rest of the calculation, which is something that we did on last Thursday. The main point is that if you do the calculation, you will find that the acceleration now becomes, depends upon, for the first time, not only your small m, but it also depends upon big M. It actually depends upon how massive the wheel is. In fact, we know very well that it will come down slowly if your wheel is a very, very heavy wheel, massive wheel. The other problem that I did last time, which is worth going over, is a ball rolling down an incline. Any questions so far? Everything we have done, by the way, is very non-trivial. It's not at all simple. I want you guys just to be cautious when you do these calculations, because chances of going wrong are indeed very high. All right, so let's do the inclined plane study one more time. And here we have, let's say, whatever ball or sphere, doesn't matter. And this thing is coming down, okay? This is an incline, and the angle of the incline, let's say, is theta. So it has a mass m. So therefore, just like before, acceleration is A, let's say, center of mass acceleration. So I can write down a force equation. That is the first thing I should do, let's say. And the force equation should be, and also this is a rough enough surface such that I have a friction force, and we know that's a point contact, so the friction force is characterized by a static friction force, which is very counterintuitive because this thing is moving and we are used to regarding that as kinetic friction, but for the reasons I told you, that we have a rigid body, we have a single point contact, this thing turns out to be static friction for that reason. Don't mess it up. So I know already that this is my mg, I know this is theta, so therefore I can break it down like this and like that, just like I've done earlier. So therefore the downward force is mg sine of theta. Whatever value of theta you can put in, whatever value of mass you can put in, minus there is a static friction force Fs, which looks very counterintuitive, but that's what it is. And then you have the mass times the acceleration of this sphere, or disk, whatever, doesn't matter. So that's your first equation. Remember, we have three equations to set up here, just like in the last case. Now we will do the torque equation. And this is new for you guys, so let's do the torque equation very carefully. So the torque equation is going to come around, just like here, for example, you saw that it was the tension that was tugging the wheel. Here the rotation is possible only because there is this, in this case there is a static friction that's able to link with the forward motion. So static friction being present potentially means that you can relate this acceleration here to the rotation here. So it turns out that if you look at this thing here, at this contact point P, there would indeed be a static friction force that it will feel momentarily. And there is a distance r, which is the radius of this. So as far as the center of mass velocity is concerned, so this is really the center of mass velocity. So we have to be very careful, or center of mass acceleration, whatever we call it. So we can be a little bit careful and call it a center of mass because it's only r. Then we should be able to write that this Fs, the static friction force, times r should be equal to moment of inertia I times alpha. And this I, by the way, because the rotation is about the center of mass, this moment of inertia is about the center of mass. Moment of inertia is about this point, the axis passing through this point, and it's rotating about that. I told you that you can take moment of inertia about different points, right? For example, different axes. For example, I told you that you can have a disk that is rotating about the axis at the center. You can also correspondingly have a disk that is rotating about an axis away from the center. In fact, we did a theorem, parallel axis theorem, that gave you the capacity that if you know this moment of inertia about the axis, you can find out the moment of inertia about some other point that is a distance d from this axis. In fact, you add md squared. Yeah?
So any force that's like perpendicular to like the radius of the circle, you multiply the radius times that force, that gives you the torque.
Right. So the key word is perpendicular, right? Why? Because remember, I gave you guys the formula for the torque, right? The formula for the torque was so this is just the magnitude of the torque, okay? F times r times sine of theta. So r sine of theta effectively means the perpendicular distance that the force makes with the point of rotation. So I'll come to this point. In fact, I have assigned one of the homework problems where this thing comes into play, because if I assigned a problem where I have a plate, and this plate has forces acting on it like so, and another force is acting like that. I don't remember which problem number it is, but it's a relatively straightforward problem. This is the axis of interest, okay? So this force can be translated forward, which means the perpendicular distance is this distance. Because force is a vector, it can be moved that way, that way. Same here, the perpendicular distance is this distance. So if the side is A, this is A over 2. Okay? Now look at this guy though. This guy, on the other hand, can also be translated, but this guy is moving in an angle, which means the perpendicular distance would be this. Half the diagonal. Okay? So how do you effectively calculate this F times R times sine theta? You take your F, but then you seek your R sine theta. And you do not necessarily have to make the R touch the F as drawn, because the force can be translated, vectors can be translated. If I tell you a force is being applied this way, it is actually the direction and the magnitude that matters, right? So that's very important. In this case, the direction and the magnitude matters, but with respect to which axis will also matter. So you can't really move the force that way, because that will change your R, but you can translate it forward or backward as need be. So here, therefore, the torque is coming from Fs, and Fs times R is going to give you I alpha. And again, A, center of mass, is R alpha. So that's your condition 3, and this obviously is your condition 2. So with these 3 conditions, you are now able to solve whatever is needed in this problem. So I don't need to go any further, because I've already done this problem actually Thursday. If you look at your notes, you'll find I've done it on Thursday. But I want to emphasize the fact that how you set these up. You set these up by first constructing the force equation, which you can do now. This is the newbie here, the torque equation. And this also is very simple, that you shouldn't have to fumble on, as long as you remember that you have to apply the no slipping condition in most problems, unless I specifically tell you that it is icy or there is no friction or some such thing, which means this condition no longer remains valid. So at this point, the next thing that you do is you replace what I is. So let's say I, in general, is some beta mr square, but this beta depends upon the shape. For example, it's a sphere, and then your beta is 2/5, like we did before. For example, it's a disk, then your beta is half. So you stick that in, right? Then you'll find one of these r's will go away, and everything we have done there pretty much repeats itself. So the point is that what is the strategy that you must use to solve these problems? And the reason why I'm spending so much time today is because now you have a few different tools that you need to use. And I don't want you to fumble on these tools, because then you will not be able to proceed further at this stage. Let's consider the problem. It's a very famous problem. The problem is that of let's say you have a vertical wall, and here you have your ground, and you are trying to climb using some ladder. So that's your ladder. And obviously, you don't want your ladder to slip, because then you might fall. So this becomes a problem where you have forces acting, you have torques acting, and you have to have effective force and torque go away, because otherwise the system will not be stable and you will get hurt. So first, let's not go up the ladder. Let's see what forces are at play. So this is far from simple. So this guy has a mass. So let's say it's a uniformly distributed mass, and so we can imagine there is a center of mass, which means that there is a downward acting force, which is my weight. So I have an mg acting downward. Because of this mg, this ladder is expected to be pressing both here as well as here, right? It's expected to be applying some pressure at both these points. Now, we don't really know what kind of force will be the reaction force because of Newton's third law at this point and at that point. We don't know that. That depends on a lot of things. So in reality, this force may be that way, and that force may be this way or something. In reality. Okay? So it's clearly complicated. We don't know what to do with it. So let me show you the trick. The trick is that no matter what the direction, in general you assume that there are two forces here. One force is going that way, and one force is going this way or the other way. It doesn't matter for now. And likewise here, one force may be going this way, and one force may be going that way. We don't really know what's happening, but it is safe to say, nobody can blame us, if we just say that, okay, this is what's happening. And for now, let's forget about the complexity associated with these reaction forces at the walls. That's why these problems are difficult, because there are micro steps involved that you must go through. Now, this friction on the floor turns out to be far more important than the friction here. Not to say that the wall friction isn't important, but the wall friction is not as critically important as the friction on the ground. So let us go to the second step of simplification. We will ignore wall friction because this would be a frictional force. All right. If you want to take into account wall friction, you still might be able to work it out, but let's simplify life. So we have two forces that are normal to the surfaces. This surface is a normal force. Let's call this N1, and this surface there is a normal force. Let's call this N2. Okay? let's conveniently label these guys. Let's call it A here, let's call it B here, and let's call it C at this point. Whenever you have geometric objects, geometric figures, geometric shapes, it's always convenient in physics and math to be able to label them. So, as I told you, the friction here is more important than the friction there. So this ladder will have a tendency to slip outward. Imagine you climbing up here. The first thing you'll worry about is that you don't want this ladder to fall. Chances are, even though in movies it falls like that most of the time, chances are that if you're really going to fall off a ladder, it's probably going to go that way. Which means that there is probably going to be a friction force F that way. If our friction force direction is wrong, we will figure out it's wrong because that will come out in the calculations. So let's now look at the forces. In particular, we look at the forces responsible for equilibrium, let's say. Because it has to be in equilibrium. You don't want this guy to fall. Responsible for equilibrium. It's actually not that difficult because you can see N1 is a horizontal force going to the left and F is a horizontal force going to the right. Therefore, I can always write F minus N1 since I can't find any other horizontal force must therefore be 0. It doesn't matter if they act in the same point because forces are translatable. We are just talking forces, not torques. And likewise, I should be able to write N2, which is upward minus mg, must be equal to 0. So you see, without even doing any work, I have, simply by observing, two equations that pop out, which are force equations. So this is the force equation along x, right? And that's the force equation along y. So in all these problems, this is going to be an important, necessary step to follow. Now you have torque equation. So this is the harder one. So let me show you some ground rules of how to do this. In a system in equilibrium like so, you can take torque about any point of your choosing. So suppose I don't tell you about which point you should take torque in your problem. You can figure out whatever point you want based upon whichever is the easiest thing to do. How cool is that? So in this case, I know that torque is force times perpendicular distance the force makes with respect to that point. If the perpendicular distance is 0, that means my torque term is dead. So which means it is strategically smart for me to pick a point about which to take the torque through which most torques go away. That simplifies my life enormously. So in this case, let me take torque about C because I see some forces passing through C. In fact, there are two forces that are passing through C. Let's say I also need to know an angle here, so I'll have to give you some more information. But for now, if I take the torque through C, this mg force, this mg here has this perpendicular distance with regard to C. So I need to have some information about the lengths here and so on and so forth. But let me not put in numbers. I just say one of those torques is going to be mg times the distance CB over 2. That's going to be one torque because the idea of this torque would be this is the force and this is the point about which this force is generating the torque. And therefore, if you just look at this, this will generate a tendency to go in the clockwise direction. So therefore this is going to be a clockwise torque. And if I take anti-clockwise as minus, I can take the clockwise with the anti-clockwise as plus, I can take the clockwise with a minus sign. So this is going to be a torque. As far as friction is concerned, friction is passing through point C. So friction force here will not give me a torque. As far as this normal force is concerned, this normal force will also not give me a torque, because this normal force also happens to be at the end of the ladder, but the ladder touches the ground. So therefore, I haven't drawn it with due diligence, but this normal force is right here. So it passes through C, and therefore that doesn't give me a torque either. So by choosing point C, I have therefore killed off torques from this force and from that force, which simplifies my life. Less calculation, chances are less error you have. More calculation you do, more error you make. That's always the law. All right. So now you see the other force we can't get rid of is this N1. So this N1 is at, if I extend this N1 is at this distance, which means at distance AB. All right. So that's going to give me a counterclockwise motion, which means it's going to be plus N1 times the length of AB. And then, if only these two torques cancel out, will I have my equilibrium condition satisfied. So therefore, in all these problems, rigid body equilibrium problems, I'll have three equations that come into play. Two force equations, because they're two-dimensional problems, and I'll also have a torque equation that comes into play. Keep in mind that as far as the torque equation is concerned, about which point you take the torque is really important. Any questions? Yes? Say it again. You don't know yet. So we have to solve it, right? Because N2, well, yes, in this case it will come out so, because equation 2 will already give you that. But in general, you don't know yet if there is more than one. For example, now if you climb up on the ladder, you have both that mg and your mg, so your N2 will now increase. N1 will depend obviously on the friction force. In this case, friction force is easy to see because it will just have to balance N1. But in reality, remember, I have dropped the possibility of any friction on the wall. That has simplified my life. There is always some small amount of friction on the wall. It's not as much as on the ground. So I've simplified this problem just so that we can get hopefully a very good understanding of it at this stage before it becomes too confusing, because these problems really can be quite challenging for students when they learn it for the first time and when they learn it in a rush. Let's consider another problem, which is a very standard problem. Let's say you have a wall, some window, let's say, and you have hung something from the window, which is like a square plate or a rod or whatever. So let's say it's homogeneous, so therefore it has some mg. Let's say the mass of it is small m, so therefore there is an mg acting downward. That's not a surprise, right? Now suppose you get creative and you put a nice flower pot here at the edge or near the edge, whatever. And this also has some mg, let's call it big M times g. All right? Now at this point you have nothing to help you, because you have put in downward forces and no commensurate upward forces, which means the whole thing is going to fall. So how do you prevent falling? Well, the only way is that you get it stuck to your wall well enough such that it doesn't fall, which means that this thing will have to go into the wall somehow. Details aside, that means there has to be some kind of an upward force that will have to come from the wall. while this is in principle possible, typically the upward force here that you can generate is not all that much. Okay? So a lot of times you'll find that when you have something like this jutting out, there may be another string or a cord that holds it. May not be, but maybe. So let's consider the scenario where there is a string or a cord holding it. So if this is a string, as we have done before, let's say this is a massless string, so it carries a force, so there's some tension T, and once before we have small mg, and then we have our flower pot, big mg, and so there is T here, and let's say this is a theta, and I told you that there is a vertical force here already at play, but now you see, because I put this tension T, I'll have to break it, let's say, in upward and sideways forces. So this sideways force will now have to be balanced by another sideways force from the wall. So let me call this piece H sub y, horizontal from wall, and H sub x, horizontal from x. So the force equation is quite simple, but not as simple as before. The downward forces are balanced by the upward forces. Upward forces at Hy is upward, and then we have T sine theta. These are upward forces, minus mg, minus big mg, and that must be in equilibrium. That must be zero. That's one set of equation I can immediately cook up, and this is for my vertical axis. So let me remind myself that we put in a y. Similarly, I can put in x. X is very simple because h sub x is to the right, so let's take it as positive, minus t cosine of theta, and this must also be 0, so that is for x. So I have equation 1 and I have equation 2. Now we have to do the hard one, the torque equation. So the question is, about which point should I take my torque? Because I want to take my torque about the point through which most torques will go away. Now, assuming that this big M and this at the same point, there are three forces here, this one, and that one. And over here, there are two forces, this one and that one. Well, this one too, because if you translate that, it will go through this point here. So therefore, you have three forces that pass through this point and three forces that pass through that. So it's a toss-up. You can take either this point or that point about which you want to take torque. So let us say I want to take torque about this point here. Call it O. Let's call this point A, and let's call this point B. So then the torque about this point by mg would be mg times, it's the middle, so AO over 2. Whatever is the length of AO that's given in the problem, divided by 2. And this torque is going to be clockwise, which means it will be minus. Okay? Same happens with big mg, so minus big mg, but now it's just AO, because it's at the edge. And T sine theta is going to be upward, so that's going to give me counterclockwise torque plus T sine theta times AO. And all of these should cancel out to 0. This point doesn't generate a torque, this force, because this force passes to this point, and Hy doesn't generate torque, Hy passes to this point, and T cosine theta, if you extend it forward, it also passes through this point. So therefore, there is no other torque that will be non-vanishing from the other forces. I'm going to continue this discussion on Thursday before we move on, because as you can see, this chapter is challenging. There is quite a bit of learning curve. My hope is that you guys will actually try to work on the homeworks by Thursday. So as I discuss these problems, if you have issues, you'll be able to ask me and I can address them. All right, let's go to the quiz.